Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Today we're going to talk about solubility and double displacement reactions. So first, what is solubility? Every time we put something in water, it will dissolve, but the extent varies. So the ability for solute to dissolve in a solvent from a solution is called solubility. Usually it's in the unit of gram per liter. For example, if we take a look at this white powder, it's silver chloride. The solubility of silver chloride in water is 0.00188 gram per liter at 25 degrees Celsius. Usually, if the temperature increases, the solubility will increase. So when we say solubility, we indicate the temperature. And for our good friend salt, sodium chloride, the solubility of sodium chloride in water is 357 grams per liter and 25 degrees Celsius. So if you compare these two, both of them can dissolve, but the extent varies. Since the solubility of silver chloride is so small, it's 6 orders of magnitude smaller than sodium chloride, we say silver chloride is insoluble compound in water. Instead, sodium chloride is soluble compound. In the textbook, table 4.1, we have, it summarizes the solubility rules. So you need to remember this table because in the exam, a question can show up and ask you which compound is soluble, which one is not. If you take a closer look at this table, there are two groups of compounds that are either soluble or insoluble. So the first part is all common compounds of group 1A ions, ammonium ions, or compounds with nitrate, acetates, and perchlorates. All of them are soluble compounds, and to be more specific, soluble ionic compounds. There is no exceptions to it. And for insoluble part, all common compounds, ionic compounds, including carbonates, chromates, and phosphates, are insoluble. However, there are a few exceptions, as we mentioned in the top part. So please remember this table 4.1. After we know the solubility rules, and remember when we mix two things like two chemicals in water solution or other solutions, reactions may occur. And one type of reaction is called precipitation reaction. Telling from the name, precipitation reactions means the reactants have high solubility, while at least one of the products is insoluble and precipitate. For example, if we mixed two solutions together, one is silver nitrate, the other is sodium chromate. If we mix these two together, boom, we have the product, which one of the product is a solid, silver chromate. So if we write out the reaction, it shows up like this. 2 silver nitrate react with one sodium chromate to produce silver chromate, which is insoluble product, and sodium nitrate, which is soluble. Because of this insoluble compound, it's a precipitation reaction. And you can see after each reactant or product, we put the status of this compound in parentheses to indicate which status it is. AQ means aqueous, S means solid, L means liquid, G means gas. Since the reactants are soluble, so both cations and anions are floating around in the solution. If you take a look at this equation more carefully, the two reactants actually exchange their ions. Then we have two new compounds formed. So precipitation reaction, because of that exchanging of the ions, is a double displacement reaction or metathesis reaction. For a double displacement reaction, both reactants are ionic compounds, and they exchange their ions to make two new compounds, as shown here. Besides this precipitation reaction, we have another type of double displacement reaction, which is acid and base reaction. Let's talk about acids and base first. So, and what we say here is Bronsted acids and bases. Here is a vinegar. I guess you're familiar with that. Vinegar, in other words, is acetic acid. So CH3COOH. When we dissolve this compound, acetic acid, into water solution, it's a weak acid, so it partially dissociates. But for the part it dissociates, it gives us hydrogen protons, hydrogen ion or proton. So an acid, by definition, it's a substance that produces hydrogen plus ions when dissolved in water. Anything can give you hydrogen plus, it's an acid. Okay. Actually, in the water, the H plus does not exist just by itself. It will combine with the water molecule and give you a H3O plus in the aqueous solution. But usually we simplify that chemical formula and just write H plus. Okay, and this H3O plus is called hydronium ion. Okay, all the hydrogen plus in the water were existing as hydronium ion. So because hydronium ion can be split as H2O plus H plus, and that H2O can cancel out before and after reaction. So usually we simplify the hydronium ion as H plus as a product. Here we have a bowl of a chemical. Does it look familiar to you? It's caustic soda or sodium hydroxide, NaOH. So when sodium hydroxide dissolves in water, instead of giving hydrogen, it gives us hydroxide. So a base, by definition, is a substance that produces hydroxide ions when dissolved in water. So the definition of an acid and base is very clear. Now, if we put an acid and base together, then we have an acid-base reaction. For example, here is an acid-base reaction. As a reactant, we have an acid, HCl, and a base, NaOH. As a reactant, we have a salt, sodium chloride, and water. So, an acid-base reaction refers to a reaction that only has an acid and a base as reactants and produces a salt and water. And as you can see, an acid-base reaction is also a double displacement reaction. The hydrochloric acid exchanged the chloride with the hydroxide. So we now have a water and a sodium chloride. So it's still a double displacement reaction. When reacting stoichiometrically, this process, the acid-base reaction, can be called neutralization. So on the right, I indicate the table 4.2 about strong and weak acid and bases, so you can know which one is acid and which one is a base. So not only strong acid and base can react with each other, weak acid and base can also react with each other, or weak and strong, they mix each other, can still react. When you balance in acid-base reactions, there's a trick you can do is to match the number of hydrogens and hydroxide, hydrogens from acid and hydroxide from a base. So for strong acid and base reactions, match the number of hydrogens and the number of hydroxides, exchange them to produce salt and water. Also, if we have strong or weak acid-base reactions, when weak acid or base is involved, follow the same procedure. Okay, determine the number of hydrogen from an acid and match that with number of hydroxide from a base. exchange them to make a salt and water. Both of these reactions are reacting stoichiometrically. And in the experimental chemistry, we can use that and use an indicator to use an acid to titrate a base, or use a base to titrate an acid. The titration reaction refers to the acid-base reaction that exactly follows the stoichiometry calculation and is a neutralization reaction. Let's take an example to solve a titration problem. Calculate the molarity of a solution of potassium hydroxide if 18.15 milliliter of it is required for the titration of a 20.00 milliliter sample of a 0.2452 molarity of nitric acid solution. First, it's a titration problem. We need to write out the chemical equation. So it's KOH reacting with NHO3. We balance the equation, 1 OH reacting with 1 H, so it's 1-to-1 ratio. The product is water, and by exchanging the anions, potassium nitrate. And it gives us information of the acid. So for the stoichiometry calculation, I suggest you to convert everything into quantity first. So we can convert the acid 20.0 milliliter sample of 0.2452 molarity into moles. So then we can calculate the moles of nitric acid that is consumed. Moles equals to molarity times the volume, and the molarity should be in the unit of liter. Now it's in the milliliter. So we need to convert the milliliter into liter first, and then plug in the equation, get the moles of nitric acid is 4.904 times 10 to the minus 3 mole. Okay, so once we know how many moles of nitric acid is consumed, then based on this chemical equation, it's reacting stoichiometrically, so we can calculate the moles of potassium hydroxide that is needed. Then from that, using the moles and the volume potassium hydroxide, we can calculate the molarity. Okay, let's do the stoichiometry calculation first. Assume X mole of potassium hydroxide is required. Then we can establish the ratio, 1 mole of potassium hydroxide to 1 mole of nitric acid. That equals the X mole in reality, how much is consumed, and 4.904 times 10 to the minus 3 moles of nitric acid is consumed. Cross multiply, solve this equation, then X, the moles of hydroxide, equals to 4.904 times 10 to the minus 3 mole. All right, now we have the moles of potassium hydroxide. Then we can calculate the molarity of potassium hydroxide, converting the milliliter to liter, and then calculate the molarity of the base. Plug in numbers, the answer is 0.2702 mole per liter, or molarity. All right, this is the end of this video. See you next time.